Hello, welcome to part 4 of Physics Paper 1. Okay, I'll just get started straight away. So this was the gravity thing. It was about the students dropping. So let's have a look at the full explanation. So measure G due to gravity, and measure T for a small steel ball to fall through a height. Okay, so that was last time. We'll recap. So the timings were 0.74, 0.69, 0.81. So to calculate the average time, so all you do is add all three together and divide by, let's turn the pen on, so 0.74 plus 0.69 plus 0.81 and divide that by 3, okay, and 0.75. Okay, so that's where you write the answer. That's it, okay, just an average. So explain one way the students can improve their procedure to obtain a more accurate value of G. Okay, so you could use an electronic timer or light gate. To use an electronic timer. Or light gate. To eliminate, so it means get rid of human error. So human reaction time, I'll say a bit more precise. Reaction time. Okay. A car traveling at 15 meters per second comes to rest in a distance of 14 meters where the brakes are applied. To calculate the deceleration of the car, using equations selected from a list of equations at the end of this paper. Let's go to the end, so it's the last page. So final velocity, so it's anyone with movement. Final velocity minus initial velocity, 2 times acceleration times distance. So it's this one, v squared minus u squared 2ax. Okay, let's go back. Oh, we've gone far enough. Let's go. We're going back to where we were. We've done those ones. So we're a bit further along than I thought. That's fine. Okay, yeah, we're here. So v squared minus u squared equals 2ax. The short way of writing that. If the numbers are together, that means they're times. So we want to calculate deceleration. So acceleration, deceleration, actually the same thing. Deceleration is negative. So we need to rearrange to make a the subject. So all we do is divide both sides by 2x. So we get a on its own, just put a over here, v squared minus u squared, and then over 2x. So this carries on from v squared 15 squared u squared. Okay, so actually, it's a little bit of a subtle thing here. Let's just get rid of that minus there for a minute. So the final speed, so car traveling at 15 meters per second comes to rest. So the initial speed is actually 15 squared. So it doesn't really matter, but I was going to make sure just for clarity, I'm going to point something out to you. Okay, so actually v squared is the final speed. So actually it's 0 squared minus 15 squared. That's where the negative acceleration comes in. Okay, you could put it at the end manually. There's ways of doing this, but we'll put it there for now. 2x. Distance, x is distance, so it's 14. So 2 times 14, I'm sure you know it's 28. So we have to do minus 15 squared, which is divided by 2 times 14. So we actually get, it comes out of this, 8.04, and it's a minus, it's a deceleration. Okay. So deceleration's got a minus in front of it, and we don't even have to work out units because they're already there. Okay, next one. Which of these is a non-renewable source of energy? Okay, so geothermal is renewable, it's boxed under the ground. Natural gas, non-renewable. Okay, it's obviously going to be that one, isn't it? Tidal is renewable and solar is renewable. So renewable, remember, means that it won't run out. So non-renewable means it will run out. Okay, part B. Explain why renewable sources provide an increasing fraction of the electricity supply for many countries. I mean, most of this is to do with the decrease in non-renewables, really. So it's a decrease. Okay, decrease in non-renewables. Okay, as coal, oil, and gas emit carbon dioxide. Okay. So renewables don't emit CO2 and don't contribute to climate change. So renewables do not emit carbon dioxide and do not contribute to climate change. Okay, that's what there. So next one. Electricity can be generated using a water turbine. Water gains kinetic energy by falling from the top of a dam. Calculate the minimum height that 7 kilograms of water must fall to gain 1,300 joules of kinetic energy. Okay, so this one. Okay, so we've got kinetic energy, okay, and height. So height is always going to be GPE. Equals mg delta h. Okay, m is mass, g is gravitational constant, and h change in height. Okay, so we've actually got GPU, we've actually got the energy, because joules is always energy. Okay, mass is 7 kilograms. G is 10. We don't know the height, so we'll leave that. Again, we're rearranging 1,300 divided by 7 times 10, obviously that's 70, is equal to h. Okay, so if your answer rounds up to 19 meters, that is the correct answer. So next one, as water enters the turbine at the bottom of the dam, the kinetic energy, so kinetic now again, of 8 kilograms of water, moving water, is 1,100 joules. Calculate the speed of the moving water as it enters the turbine. So speed, we're going to have kinetic energy. So K is half mv squared. Half is just a number. Again, we've actually got the energy. Okay, I'm going to write as 0.5 just to show it's a number. 8 kilograms, we've got a different amount. V squared. Okay, so the first thing, rearrange 1100, just numbers. So 0.5 times 8 is equal to V squared. So we want square root both sides. 1100, 0.5 times 8 equals V. Okay, so when we do that, we'll work that out. Okay, we get an answer that rounds to 17. Okay, 17. So we've got that. Okay, move on. Okay, so moving air can be used to generate electricity using a wind turbine. Okay, so figure 8 is a graph of kinetic energy against wind speed for a mass of moving air. Okay, just before the air reaches a wind turbine, it has a wind speed of 15 meters per second. When the air has gone through the turbine, it has a wind speed of 30 meters per second. Okay, as the air moves through the turbine, some of its kinetic energy is transferred to the turbine. Use the graph to determine the percentage of the kinetic energy transferred to the turbine from the air. Okay, 15 and 13. So on this graph, each 2 squares represents 1. So we've all got 15 there. Okay. And then 4 squares. 1, 2. So 1, 2, 3, 4. So we have, so let's read across. So we've got, let's go across here, 5, okay, and 4, okay, 5 and 4. I mean, that's quite straightforward, isn't it? Okay, so 5 minus 4 is also going to give us 1. So it's lost 1. What's the unit there? It's a good one, isn't it? Kilojoules. Okay, 1 kilojoule. Okay, so what's the percentage? You probably can do this in our heads actually. It's 1. So the percentage 1 over 5. So it's the biggest one. It's like we're doing out of a test, isn't it? 1 over 5. Okay, that gives us 0.2 for maths. To get a percentage, we times by 100%. So you get 20. Again, that answer at the end there, I'm going to write 20 here. That depended on how you read your graph. Okay, I actually read the mark scheme and they actually accept answers between 18 and 32. So quite a big range of answers. Okay, for that one. In the exam, it's a bit easier because you're right in front of the paper and you get your pencil and you draw across. Okay, across to the, what you do. Number 8, a student investigates how different surfaces radiate energy as they cool. Figure 9 shows some of the apparatus used as a part of the investigation. Hot water and copper set up in a pot. Describe how the student could collect data to show how the rate of cooling of the container and water change with time. So let's have a look. So it's actually a very easy, straightforward question. You need a temperature sensor or thermometer. So use a temperature sensor or thermometer. The temperature sensor, thermometer. Okay. Then measure the temperature at regular time intervals. So that's actually a key point to get in the marks here. Is measure the temperature at regular time intervals. That means sort of the same time intervals. Time intervals. So I would say at least 10 times. Okay. So figure 10 is a graph of intensity against wavelength for the electromagnetic radiation emitted by a halogen lamp. Okay, so most of it's not in the visible. Okay, intensity. And describe how the intensity, sort of how strong it is in a way, of the radiation varies with wavelength, figure 10. Okay, so the intensity has a peak. Okay, has a main peak and several smaller peaks. A peak on a mountain. A mountain peak. It was like a mountain, isn't it? And several smaller peaks. So as a main peak and several smaller peaks. Most is in the non-visible spectrum. Just let the page go down a bit here. The non-visible so we can't see most of it. Okay, so I probably might be in infrared there, but we don't know. We just say non-visible. That's what we know. Okay, figure 11 is a graph of temperature this time against time for a halogen lamp for the first 120 milliseconds after it has been switched on. Okay, so temperature in degrees Celsius, time in milliseconds. Calculate the gradient of the graph at a time of 30 milliseconds. That's important, that unit there. Right, let's look at 30. So this one, so 22, 4, 6, 8. So 2, 4. Okay, so that's going to be right in the middle there. 30. Then to get the gradient at that point, we need to draw. Right, we need to draw a tangent. Okay, we need to draw a tangent. So it's a straight line, as straight as we can. Okay, so let's draw it up like that. So it's like a triangle. Okay, to get the tangent there. So that distance there, okay, is 150. So it's going up in tens, 150, 160, 170. Let's just mark that. Okay, let's just go to the top, 250. So I'm going to make this a little bit neater. And that here, so let's have a look. So that was 42 at that end. And that end is, let's go down, way down here. Which one is that possible? 2, 4, 6. Okay, so we've got a delta y and a delta x. So delta x, so much the x has changed, 42 minus 6. Okay, so that is 36. Yeah, so you have a moment there you can't work something out. So I think you always have a calculator in these exams. Delta y, okay, delta y is this one, 250 minus 170. Okay, so you've always got a calculator, so don't worry about working that out in your head. Okay, so let's get a calculator. So 250 minus 170. Okay, oops. 250. Always, yeah, reset your calculator is another rule. So, okay, it's 80. Okay, and let's do the gradient. So gradient, okay, gradient is delta y over delta x. Okay, so delta y, 80 and 36. Okay, so let's just work that out, because obviously it depends on where you drew your graph. So it shouldn't vary too much, but just very little bit, depending on where you drew your graph. Okay, 2.2 recurring. We're going to put 2.2, round it up. Okay, so let's be careful with the units here. So 2.2 degrees per millisecond. Oh, degrees. Celsius per millisecond. Okay, so we've got to be careful. It's quite a difficult one. We've got to be careful of the units. Okay, so the gradient, and once we state our unit 2.2 and then degrees Celsius per millisecond. Okay, that's fine. You could do it per second, but you have to times it by 1,000, but that's exactly the same thing. Okay. Okay, so explain why the temperature of the lamp rises and then remains at a constant value. Okay, so again, this is one that's not always well answered, okay, by students. I've seen lots of questions like this. So let's just think about it together. So the temperature rises. Why does it rise in the first place? Okay, the temperature rises because the rate of energy being supplied to the lamp, let's write this down. So the temperature rises as the rate of energy supplied to the lamp is greater than the energy being lost or radiated. Okay. Right, okay. So at a constant temperature, that gives us the next explanation then. So at a constant temperature, and we've got the flat bit of the graph. Okay, constant temperature, energy is being radiated at the same rate as it is being input. Okay, so at a constant temperature, radiation is being lost at the same rate, okay, at which it's supplied. So it's being lost at the same rate as supplied. So apologies there, you may have heard my cat. He's very interested in what I'm doing. Okay, so I'm just going to end the video there. Okay, and I'll see you in the next part. So thank you. Goodbye.